Okay. I have a little time today, so we're still gonna have to go slow because everything's starting to just get much harder. So yesterday or last time, we implemented a system call and created this test program here to exercise that system call. It was just a sum number with system call ID 300 for our x86 64 architecture. Um, I think what I didn't do correctly was I had logging in that system call, and I wanted to actually see that in dmessage, but I ended up having a typo in there with the comma in that print case statement, so I had to recompile the kernel. I did that and I loaded it up and everything, and I just wanted to show you like that print statement does indeed work. So we do cd desktop and then just run our program again. So we did the some system call, and then we could just check the message, and then we'll actually see that we have the logging here now. I ran it before just to make sure, but this is what we logged out exactly. Average dev system num received two args. We had 2004. So our first system call. I mean, good. That's great, right? So today we're going to continue on reading the book. We're doing kernel data structures. So we talked about linked lists a little bit, but I think here is where it gets really hard because the Linux kernel does data structures slightly differently. Different from like the linked list in the kernel is not the same linked list that we usually use in terms of like having it having let me just try to draw this. Okay, so like our typical linked list node is like this, right? Where we have data and then a next, and that next points to like another node that has data in there, and then next. Okay. So data is actually contained inside this struct. Okay, so this is like a struct, and this is contained in struct. Okay, the kernel in this case is different. This here is the data, and then we just have basically a next inside as one of the properties going to um, the next node. So these are just next, and then it just so happens that the data, yeah, let's just do this. The data is separate from the node, but it's always in. This is your true data. See, even I'm having a hard time. This is the true data, but we have a separate next pointer that leads to the next node, and then what you had to do is you had to calculate some offset math on memory locations to actually get the real piece of data contained by it. So it's different. It's hard for me to explain, but then once we start reading and doing things, it'll be clear. I'm having a hard time explaining it because I'm still learning this myself too. It's like the first time I ever seen data structure like done the way like this. So yeah. Okay. So in comparison to most linked list implementations, including the generic approach described in the previous sections, so basically like the way we think about it right here, the typical linked list, the Linux kernel's implementation is unique. Recall from the earlier discussion that data, or a grouping of data such as a struct, is maintained in the linked list by adding a next and perhaps a previous node pointer to the data. For example, assume we had a fox structure to describe that member of the Canidae family. So struct fox, then we have three properties. We have a tail length, which is a long, O8, which is a long, and then is fantastic, which is a bool type. Okay, so here's a common pattern for making it a list of foxes. So we will usually do something like this, where we actually add a reference, a pointer to the next struct or the previous struct. So the common pattern for storing this structure in a linked list is to embed the list pointer into the structure. For example, we'll have two of these structures, right? Like it's this struct fox, and we'll point to other struct foxes, and the next and the previous pointers. So this is what we're used to. This is what we're used to. The Linux kernel approach is different. Instead of turning the structure into a linked list, the Linux approach is to embed a linked list node in the structure. Okay, so this linked list node is actually generic. It has nothing to do with the struct. So we're used to embedding the struct itself, a reference, a pointer to the struct. So maybe my diagram was not correct. Maybe we should think of it like this. Maybe we should think about the normal way to do this is, let's just say this is a fox, okay? And we can just say this is another fox pointer to another fox. And this is another fox pointer to another fox. And then we'll just say this is null. Okay? So we're just embedding other pointers to other structs in this case. So this is data. So that's the way we do it. So these are actually, we like to treat them as like next pointers, but really they're just pointers to the entire fox struct, or the entire struct that you have. So in this case, with the Linux kernel way of doing things, we aren't going to have pointers of that struct type embedded inside the struct. Instead, we'll have generic pointers that just point to some arbitrary generic pointer elsewhere, and then we had to do some math to calculate exactly what data is there. So the linked list structure. In the old days, there were multiple implementations of linked lists in the kernel. A single powerful linked list implementation was needed to remove duplicate code. During the 2.1 kernel development series, the official kernel linked list implementation was introduced. All existing uses of linked lists now use the official implementation. Do not reinvent the wheel. Okay. The linked list code is declared in the header file linux/list.h, and the data structure is simple. It is just a struct that points to basically some arbitrary area in memory as a next and some arbitrary area as a previous. List head is just basically a struct that contains two pointers. Okay? I know it's hard to grasp, but it's just basically a simple structure that contains two pointers, two simple pointers. So the next pointer points to the next list node, and the previous pointer points to the previous list node. Yet, okay, here's the important part. You're looking at this and you go, this is not very useful, right? Because we don't have data. We're not used to this. We're not seeing the data here. We just have these two things here. So how do we actually even make things a linked list in this case? So they're gonna point this out. It's like, yet this doesn't seem very useful. What value is a giant linked list of linked list nodes? You have no data attached to any of these. Okay, so here's like the creative part of this linked list implementation. This is like the creative part. That's the part that I had never like thought about before. So the utility is in how the list head structure is used. So how we use it actually shows us like the power of this type of implementation. So say for example, we have this struct fox, where we have this data here, but now we have this list head list, which contains next and a previous. So we've embedded a linked list node that has no relation. It's not a fox struct. It's just its own different struct type that happens to point to has a memory location that points to another struct of its own type again. Okay, so that's the difference. We're not pointing to a Fox struct. We're pointing to a list head struct in this case. And this list head struct only has two properties, a next and a previous, where in turn they point to other list head structs. Okay, so it's this list basically becomes a property of that struct as something else. So with this, list.next in Fox points to the next element, meaning when we say next element, it doesn't point directly to the Fox struct exactly. It points to the next list head struct. Same thing with the previous, right? The previous pointer will point to the previous list head struct, not exactly the Fox struct. So we look at this in memory. Suppose that this region here is Fox, okay? Well, what that means is really this here is the list head. Let's just say take this part right here within is the list head type. It's a struct, right? And it contains inside next and the previous. Pretend these are two memory addresses now. Okay. In turn, what happens is that they point somewhere in memory to the next list head. Let me draw this better. Let me just draw the next, okay, so it's easier. Oops. Okay. Then let me also extend this diagram. Okay. And then let me do this. Okay. In turn, what they will do is they will point to the next list head. So this is the next Fox struct, and this is the next list head. So this actually points to here. Okay? Not the Fox struct, but the next thing here. Not to this next though. Let's just like that. Pretty much within the Fox struct, okay, within that Fox struct. So notice how it's not pointing to the next Fox struct, but it's pointing to the next list head. So we have to really make sure we have this clear, okay. And in turn, previous here could point to some other list head struct up here, which is encapsulated by another Fox struct. Okay. All right. So way different than what we're used to. Okay. Now this is becoming useful, but it gets better. The kernel provides a family of routines to manipulate the lists. Because it's like the outstanding question here is now, since we're pointing to these separate list heads, how do we actually access that Fox data? How do we actually access the stuff in here? Okay, this is where we have a bunch of helpers available to make that possible. Given some sort of list head here, we can actually find the data of that struct that contains the list head in this case. So for example, the list add method adds a new node to an existing linked list. These methods, however, are generic. They accept only list head structures. So only list heads. So you can only add new list heads, but it's really important to actually have this list head be contained by your specific struct type. That's the key. Using the macro, and here's the key, container of, we can easily find the parent structure containing any given number or given member variable. Okay, so what does that mean? It means that if you did container of this one, container of this here, this entire thing here, okay, if you did a container of this list head, you will actually get back this entire struct. Okay, and then that return value of this entire struct means that you can access any of the properties in here. Okay, so not too bad now. This list head thing is starting to become more useful. On its own, it looks useless, but when you start to embed it within a struct and have it point to other list head structs instead of the specific node type, what ends up happening is that now you can just reuse this list head struct in every other type of linked list that you want. It becomes generic in this case. It's one way to simulate generic programming. So then you can use the container of macro to get the specific struct that contains the list head, and then getting that thing that contains the list head, you can actually access each of those properties. So it's clever. So this is because in C, the offset of a given variable into a structure is fixed by the API at compile time. What they're saying is that it works, this container thing works because remember, structs is just a block of memory. It's just a block of contiguous memory similar to arrays, but in the order you declare properties in the struct, like int A, int B, int C, holds consistent in memory. This will be A here always, this will be B here always, this will be C always, and this will be 4 bytes. This will be 4 bytes. This will be 4 bytes. Just like an array, except that the reason why you need to access elements in the struct by their property names is because each could potentially have a different size attached to it. Whereas an array, it works with indexes because every single element is of the same size or the same length in bytes. So that's why this works, because if you put list head as the list head type as the last property of your struct, you can do some math to really get to the first starting position of your struct in the memory address. And then once you get that, you can just access the offsets here, which is basically the properties of that struct. So here is the macro container of, okay, and basically you give it the pointer, okay. So basically, you know, the what was it? Was it the list head? Okay, the type. So what is the struct that you're looking for? What's the struct containing it? And I forgot what member was. I think member was the name of your list head, because it will be like next or previous or whatever you call it. So let's see an example. Maybe this is slightly different from what I'm saying, but okay. So using container. Oh, so what else does it do here? Let's just be careful. So we do some type of, and this type cast of 0 is to basically, I think what you do is you access you kind of do some math. You're just allowing to figure out like what is the offset. So this calculation here is going to be just getting some sort of offset. And so what you can do is, given like a memory address, a set of memory addresses where it's like 0, right? 0 is like null pointer, and then you have like 1, 2, 3, 4, 5. You can just kind of like lay out your struct like this, for example. It's all pretend, really. You can start your offset at 0 to make math easier, and that's what it's trying to do. Oops. It's starting at 0, getting that member, which is next. So starting at 0, let's get next, which could possibly be here, right? So let's get next. And then I think what you can do is, so you basically then cast that and have that be assigned as that pointer, and then you do some subtraction with that offset. So Sorry, lots of notifications coming in. Okay. Yeah, so it's like this is kind of hard to read, but I think once we start writing code, it becomes easier. But basically, the only thing you need to know is that container of is the macro that gets us back the struct containing the list head. So using container of, we can define a simple function to return the parent structure containing any list head struct. So basically, list entry is that helper. It's a helper macro that basically uses container of. So you know, you don't have to use this container of semantic. You can just use list entry, and that gives you back. It's the same thing. It's just a good alias because it keeps that sort of language of that you're operating with list, and so you know, yeah, it makes it easier to understand. So armed with list entry, the kernel provides routines to create, manipulate, and otherwise manage linked lists, all without knowing anything about structures the list head resides in. Okay. So they're just basically telling you that now that you have list entry, you shouldn't really like stress too much. But I still want to know how this works. So, defining a linked list. As shown, a list head by itself is worthless. It is normally embedded inside your own structure, like so. This list needs to be initialized before it can be used. So because most of the elements are created dynamically, which is probably why you would need a linked list, the most common way of initializing the linked list is at runtime. So we basically create the fox, then we malloc using kmalloc, which is the kernel version of malloc. We take the size of that pointer, and I think these are flags for how you want to malloc it. And then what do we do here? Oh, we just set the properties. Okay, and then we initialize a list head inside as the list. We give the pointer to the list head, and then this macro here will do whatever to set up that internal list head structure of that box. Okay. Okay. So it's just directions for me to do something later. Okay. So if the structure is statically created at compile time and you have a direct reference to it, you can simply do this. Struct red fox, struct fox red fox, and we can just do it this way. Okay, sure. Same thing, I guess. Okay, so list heads. Okay. The previous section shows how easy it is to take an existing structure, such as our struct fox example, and turn it into a linked list. With simple code changes, our structure is now manageable by the kernel's linked list routines. But before we can use those routines, we need a canonical pointer to refer to the list as a whole. So basically your head pointer, like what is our main pointer that we're going to be passing around when we're manipulating the linked list? So basically the head pointer. One nice aspect of the kernel's linked list implementation is that our fox nodes are indistinguishable. Each contains a list head, and we can iterate from any one node to the next until we have seen every node. This approach is elegant, but you will generally want a special pointer that refers to your linked list, meaning your head. You want to pass around this head without being a list node itself. Interestingly, this special node is in fact a normal list head. So static list head fox list. This defines and initializes a list head named fox list. The majority of the linked list routines accept one or two parameters, the head node or the head node plus an actual list node. So let's look at these routines. Okay. Whew. manipulating linked lists. The kernel provides a family of functions to manipulate linked lists. Thank goodness. They all take pointers to one or more list head structures. So basically, you need to pass in the list head in order to even do something. Treat it like a linked list. The functions are implemented as inline functions in generic C and can be found in Linux/listh. Interestingly, all these functions are O of 1, meaning they're constant time. This means that they execute in constant time regardless of the size of the list or any other inputs. So for example, it takes the same amount of time to add or remove an entry to or from a list whether that list has 3 or 3,000 entries. This is perhaps not surprising, but still good to know. So let's see, how do we add a node to the linked list? List add struct list head, which is the pointer to the new node you want to add, and then the head of the list. Seems simple. This function adds the new node to the given list immediately after the head node. Because the list is circular and generally has no concept of first or last nodes, you can pass any element for head. If you do pass the last element, however, this function can be used to implement a stack. Why? Because you have pointers to the previous. Yeah. Returning to our Fox example, assume we have a new struct, Fox, that we wanted to add to the Fox list. We do it like this. So basically just add it like this. So we have a new struct called F, which is a pointer to, or this is a pointer to a specific struct Fox that you have created. You pass in that list node, and then you also pass in the initial head of that Fox list. And this is also a list head type, a pointer to a list head type. So to add a node to the end of a linked list, this is how we do it. Add tail. Let's add tail. So given this node and the head, I think what the head does is that since it's circular, it'll just take the previous, which is the tail, and then like splice it in to the end of the list. So that's the reason why it's called constant time. So like if you think about it in this perspective, we have something like this is going to be the head. Okay. And then we have another node. We have another node. So this is going to be the tail. But remember, it's circular. So then this is actually going to point to here. Okay. And this is actually going to point to there. So even if you have given any head, all you have to do is just add a node, like kind of just here. Okay. Make this point to there, and then make this previous point back to the previous tail, and make this next point to the head. So that's how you can do it in constant time. So okay. This function adds a new node to the given list immediately before the head node. As with list add, because lists are circular, you can generally pass any element for head. This function can be used to implement a queue, however you pass the first element. Okay. Deleting a node from a linked list. After adding a node to a linked list, deleting a node from a list is the next most important operation. To delete a node from a linked list, use list del. So this is the entry you want to delete. It's easy, you only need that because you have access to both the previous and the next list heads, so that you can just kind of like make sure it skips over this entry here that you want to delete. So that again is constant time. So this function removes the element entry from the list. Note that it does not free any memory belonging to the entry or the data structure in which it is embedded. This function merely removes the element from the list, so you have to destroy it ourselves. After calling this, you would typically destroy your data structure and the list head inside it. So for example, to delete the Fox node we previously added to the Fox list, we do list del, pass in the list head structure. Note that this function does not receive input as a Fox list. It simply receives a specified node because it doesn't need the head of the list, and modifies the pointers of the previous and subsequent nodes, subsequent being next, such that the given node is no longer a part of the list. the implementation is instructive. So it just basically sets, so given, where is it, list del right here. This is the entry. So we just pass in the previous and the next, and it just says, okay, well, the next is previous is going to be the current previous, and then the previous is next is going to be the next, meaning that it won't be the entry anymore. Skips it over. So if we had, let me see if I can just bring this out. Okay, and then let's say I put this as 3, put this as 3, going here, split. Okay, so just to illustrate the point, suppose we had a list of 3 nodes, and I'm just gonna do this just to okay, and we say this is the entry that we want to delete. If we said something like next prev is equals to prev, and then prev next is equals to next. Okay, suppose that this is prev, the prev node, and this is the next node. Okay, well, we're gonna be passing these two. So in this case, we're passing these two in. Okay, with this list del here. You see here, entry prev, which is this one, entry next, which is this one. What we want to do is we're going to take next, set its prev to be what? Next is prev, so we'll just break this and do this. Okay, and we'll say prev is next, okay, prev's next right here is going to be next, so we break that here and we're going to do this. Okay, so at that point these two are broken. Okay, and really then this actually effectively becomes isolated, so we can just delete that, because now we can follow the pointer to here, and then we can also follow pointer back to here. This becomes no longer relevant. Okay, all right, so to delete a node from a linked list and reinitialize it, the kernel provides list del init, list del init struct list head entry. This function behaves the same as list del, except it also reinitializes the given list head with the rationale that you no longer want the entry in the list, but you can reuse the data structure itself. Okay, moving and splicing linked list nodes. So to move a node from one list to another, so this is iterating and doing some various movements throughout, motions in the list. List move. So this is to take one node and transfer it to another, I guess. So this function removes a list entry from its linked list and adds it to the given list after the head element. So it becomes a second element after this head. So to move a node from one list to the end of another, it's list move tail. So this will be at the end of the list. It'll take the node here, and then it'll insert it to the end of the list pointed by head. Okay. Wait, yeah, inserts the element before the head entry because that's the tail. It's circular. Okay, to check whether a list is empty, we just do list empty given the list head. So this returns non-zero if the given list is empty, otherwise it returns 0. To splice two unconnected lists together, we do list splice. This function splices together two lists by inserting the list pointed to by list and to the given list after the element head. So to splice two unconnected lists together and reinitialize the old list, so basically splice them together and then use the list pointer as the new spliced list reference. This function works the same as list splice, except that the empty list pointed to by list is reinitialized. Whew. All right, so saving a couple dereferences. If you happen to already have the next and prev pointers available, you can save a couple of cycles, specifically the dereferences, to get the pointers by calling the internal list functions directly. every previously discussed function actually does nothing except find the next and previous pointers and then call the internal functions. The internal functions generally have the same name as the wrappers, except they are prefixed by double underscores. For example, rather than call list del list, you can call dunder list del with the previous next. This is useful only if the next and previous pointers are already dereferenced. Otherwise, you are just writing ugly code. See the header Linux list H for exact interfaces. Yeah, so I don't know. Maybe I didn't know that dereferencing is like a cost. So I'm just going to keep my code clean and just use this. Who cares? I'm learning. I'm not trying to be writing a super optimized thing, I guess. Okay, traversing linked lists. Now you know how to declare, initialize, and manipulate a linked list in the kernel. This is all very well and good, but it is meaningless if you have no way to access your data. The linked lists are just containers that hold your important data. You need a way to use lists to move around and access the actual structures that contain the data. The kernel, thank goodness, provides a nice set of interfaces for traversing linked lists and referencing the data structures that include them. Cool. Note that unlike the list manipulation routines, iterating over a linked list in its entirety is clearly an O of n operations for n entries in the list. So the basic approach. The most basic way to iterate over a list is with the list for each macro. Okay, it's a macro, not a function. The macro takes two parameters, both list head structures, and the first is a pointer used to point to the current entry. So P will be the current entry. You just need to declare it and then pass it into this macro here. Okay, and this will be the head of your list. So, okay, let's read that again. The first is a pointer used to point to the current entry. It is a temporary variable that you must provide. The second is the list head acting as the head node of the list you want to traverse. So see the earlier section list heads. On each iteration of the loop, the first parameter points to the next entry in the list until each entry has been visited. So the usage is as follows. So this is actually pretty trivial, I think, because you will get P in every iteration, but remember that's the list head. You want to do the whole list underscore entry or the container of to get the specific struct that is containing this list head. Because, yeah, why? Well, that is still worthless. A pointer to the list structure is usually no good. What we need is a pointer to the structure. See, you need to get the structure that contains the list head. For example, with the previous Fox structure example, we want a pointer to each Fox, not a pointer to the list member of the structure. We can use the macro list entry, which we discussed earlier, to retrieve the structure that contains the list head. So for example, just do this. Just use this entry with that pointer to the list, the type of that structure, and then the member name of the list inside this structure. Okay? And this will be the Fox right here. What does the Fox say? So, yeah. The usable approach. The previous approach does not make for a particularly intuitive or elegant code, although it does illustrate how list head nodes function. Consequently, most kernel code uses the list for each entry macro to iterate over a linked list. This macro handles the work performed by list entry by making list iteration simple. Okay, so now this is like another macro that actually gives you back the struct directly, it seems like. So position, head, member. So here, position is a pointer to the object containing the list head nodes. Okay. Think of it as the return value from list entry.head. From list entry.head is a pointer to the list head node from which you want to start iterating. What? Think of it as the return value from list entry. So find the list entry and then get the dot head. Or no, this is a sentence. Oh. Okay, think of it as a return value from list entry. Done. So that's the struct. Okay, and what is head? Head is a pointer to the list head node from which you want to start iterating. Okay, in our previous example, fox list dot member is the variable name of the list head structure in pause. So list in our example. This sounds confusing, but it is easy to use. Here's how we would rewrite the previous list for each to iterate over every fox node. So this gives us our fox node back. Okay, so f fox list, and then the member name of what we would find in this fox list. So list. So the member name of the struct, basically, because if we look at the definition again of fox, it's actually called list in this case right here. Right, so yeah, gotta be careful. Okay, so this f isn't populated with the specific fox struct. So now let's look at a real example from iNotify, the kernel's file system notification system. So static iNotify watch will have a pointer to, so iNotify watch is a structure type. We're actually going to return a pointer to that. iNotify handle is the function name, and then we give it inode, and then the inode handle struct. So it looks like here that we want to get iNotify watch entries, and an inode is probably the list in this case, or the thing containing the lists. iList is basically the member inside this inode struct that represents the list, I guess. Let's see. Yeah, so this is the list head. This is a pointer to the list head. This will be the member of the list. Okay. Watch will be the specific struct that you want to get back. Okay, so same thing here. This function iterates over all entries in the inode notify watches list. Okay, yeah, so that's the case. Each entry is of type struct iNotify watch, and the list head in that structure is named iList. With each iteration of the loop, watch points at a new node in the list. The purpose of this simple function is to search the iNotify watches list in the provided inode structure to find an iNotify watch entry whose iNotify handle matches the provided handle. Okay. Okay, I'm going to stop here. I think next time we're going to try to implement one of these lists on our own from scratch and try to just dive in deeper on how they really work. I think this is a good stopping point. So, yeah, thanks.